Today's topic is symmetry. This is Mrs. Dunn, and what we're going to do in this screencast is we are going to talk about symmetry. First, we're going to determine whether a graph is symmetric with respect to the x-axis, y-axis, and the origin, and we're going to do that both graphically and we're going to do it algebraically. And then the second thing is we're going to determine if a function is even, odd, or neither even nor odd. The first thing I want to do is show you some pictures of where symmetry shows up in the world. We have symmetry in buildings, in bridges, on rail lines, and we have symmetry in nature. And this idea of symmetry is if you could draw an imaginary line down the middle and fold a piece of paper in half, then you're going to have symmetry. Let's look at it algebraically and talk about this. So imagine if you were folding this graph in half along the y-axis. So if I fold the graph along the y-axis, the left side is going to match the right side. This graph has symmetry with respect to the y-axis. This also has symmetry with respect to the y-axis. If we fold this graph along the y-axis, the left side will match the right side. But this graph actually has symmetry with respect to the x-axis as well. If we fold this graph along the x-axis, the top will match the bottom. And this graph has symmetry with respect to the origin. We're going to talk about symmetry with respect to the origin a little bit more in a couple slides. But if you could imagine laying on your bed and you're looking at your ceiling fan, and if the ceiling fan rotates from the first quadrant to the third quadrant, think about what that symmetry would look like. We're going to talk about that algebraically too. But this graph has symmetry with respect to the origin as well. So this is an example of all three symmetries. And then this one only has symmetry with respect to the x-axis. Okay, so there are some algebraic tests for symmetry. To test for symmetry with respect to the x-axis, then we take the equation and we replace y with negative y, and we see if that resulting equation is the same. For symmetry with respect to the y-axis, we do the same thing, except we're replacing x with negative x. And then to test for symmetry with respect to the origin, we replace both x and y with negative x and negative y respectively. Okay, so let's look at a specific example. So here's an example. The equation is y equals x squared plus 2. And this is the graph of that equation. So look at that graph. And this is how easy it should be in your homework. Look at the graph. Does this have symmetry? Yes. And what kind of symmetry does it have? Where can you fold so that the left matches the right, the top matches the bottom, or that rotating of the first quadrant to the third quadrant? And it's very obvious that this has symmetry with respect to the y-axis. That's the fold. So you can tell that graphically, and that's it. You can graph these equations as long as you can graph them, because not all of them can be graphed. But if you can graph it in your calculator, you can look at that picture on your calculator and you can determine if this graph is symmetric with respect to the x-axis, y-axis, or origin. And this has symmetry with respect to the y-axis. Okay, now that's how we do it graphically. Let's talk about this algebraically. Now, you'll remember to test whether this has symmetry with respect to the y-axis, we replace x with negative x. Remember, that was in on this screen where it tells us if we're testing for symmetry with respect to the y-axis, we replace x with negative x. So if I replace x with negative x in the equation, where I see an x, I'm going to put negative x. You can see that done here. And when I square negative x, I still end up with x squared. So this is an algebraic proof that this is the equation of a graph that has symmetry with respect to the y-axis. Okay, so we went straight to the y-axis symmetry because that's what we saw on the graph. But if we were going to test x-axis and the origin algebraically, first of all, looking at that graph, do you think it has symmetry with respect to the x-axis? Hopefully you said no. And do you think it has symmetry with respect to the origin? Hopefully you said no. So let's test for that. To test for symmetry with respect to the x-axis, we replace y with negative y. So where I see a y, I put negative y, and that equation ends up completely different. If I'm going to solve for y, getting y by itself, I have to multiply by a negative 1 on both sides. And so this is not symmetric with respect to the x-axis. This equation is not the same as this equation. That's why it does not have x-axis symmetry. Let's try the origin. So to test for symmetry with respect to the origin, we replace x with negative x and y with negative y. And when I do that, I get another different equation. This is not the same equation that I started with. And that is why it is not symmetric with respect to the origin. The only type of symmetry it has is symmetry with respect to the y-axis. Okay, now let's turn our attention to even and odd functions. So an even function, if the graph of f of x has symmetry with respect to the y-axis, and that means f of negative x is equal to f of x, then we say the function is even. Let's look at an example. If we look at that example that we did previously, y equals x squared plus 2, this equation has symmetry, this function has symmetry with respect to the y-axis. That alone is all you need to determine that this is an even function. But we can take it one step further and prove that f of negative x is equal to f of x. Look at these 2 points, negative 2, 6, and 2, 6. F of x, let's say x was 2, f of 2 is 6, and f of negative 2 is also equal to 6. So since f of negative 2 is equal to f of 2, we say that this has symmetry with respect to the y-axis, and we say that this function is even. Okay, what about odd functions? So the definition of an odd function, if the graph of f of x has symmetry with respect to the origin, and that means f of negative x is equal to negative f of x, then we say the function is odd. Let's look at an example. So here's the picture of a graph that has symmetry with respect to the origin. Remember to try to imagine holding your finger at the origin and rotating this graph into the third quadrant. You can see how this piece is going to be rotated and reflected here. So this is an example. Here's the equation. Y equals 5x to the 7th minus 6x cubed minus 2x. Okay, so like I said earlier, all you need is a picture. And we can look at this graph and we know that this function is even because it has that symmetry with respect to the origin. But to do it officially, we use the algebraic means. And remember, to test for symmetry with respect to the origin, you switch those x's and y's with negative x and negative y. And so by definition, that means f of negative x is equal to negative f of x. So take an arbitrary point. I mean, we could do this with x and negative x, but pick an arbitrary point like -1. Since we already know the equation, plug -1 into this equation, and you end up with a +3. Now, that was f of -1. So now we want to find f of 1. So we're going to find f of 1 next. And when we plug 1 in, we get -3. So that is proof that f of -1 is equal to negative f of 1. Okay, that's even and odd functions. Good luck. Email me if you have any questions.